I'm going to enter matrix A, so I'll say A equals, I'm putting that in cell A14, and my matrix A is first row 1, -3, second row 0, 1.6, third row 2, 1. Matrix B equals in A18. Matrix B in the first row is 2, 3, in the second row 0, -1, in the third row 5.7, -2.04. Create a label for matrix 2A minus 1.7b. So 2A minus 1.7b equals, and again I need to widen my column A. Step 2 is to highlight an array. Now since A and B are 3 by 2, I need to highlight a 3 by 2 array. And I'll type the formula. Equals 2 times, remember the times sign in Excel for multiplication, matrix A, and this time what I'm going to do to find matrix A is to click on the first cell and drag to the last cell, and you see that does enter the array for matrix A. Close parenthesis. Minus 1.7 times matrix B. Click on the first cell of matrix B, drag to the last cell, end parenthesis. Now don't hit enter. Remember to complete the calculation, you hold down Shift and Control and hit enter, and it fills the cell. The result for 2A minus 1.7b is in the first row -1.4, -11, in the second row 0, 4.9, in the third row -5.69, and 5.47. This was much easier to do in Excel than by hand because of the decimals. You saw in an earlier lesson how to interchange rows and columns to form the transpose of a matrix. In this lesson, we will use Excel to create the transpose of a matrix. This operation is one that is quite important in application problems, as you will see later in this lesson. Transpose of a matrix. Find the transpose of matrix M equal to 1, 2, 3, 4, 5, 6. Since this is the same matrix M that is earlier in the spreadsheet, we don't need to enter it again. The transpose notation is M raised to the T power. So in Excel, I'll label the matrix just as M raised to the T power like this, equals. Remember that the transpose is created by interchanging the rows and columns of M. Since M is a 2 by 3 matrix, then M transpose is a 3 by 2 matrix. So we'll highlight a 3 by 2 array. Type the formula, equals transpose, parenthesis, and in the transpose parenthesis we'll put the array B1 to D2 in parenthesis. Remember to complete the calculation, hold down Shift and Control and hit enter. So M transpose, instead of having 1, 2, 3 in the first row, has 1, 2, 3 in the first column. The first row of M transpose is 1, 4, second row 2, 5, third row 3, 6. Let's look at the importance of the transpose in an application. Smith and Jones both work at a local car dealership. The following worksheet gives their gross sales in dollars for economy and luxury cars in August and September. Find the total sales for those 2 months. In the August table, we have that Smith sold $60,000 worth of economy cars and $87,000 for luxury cars. Jones sold $47,500 of economy cars and $70,000 of luxury cars. In September, we have that the economy cars, Smith sold $27,400 and Jones $89,000. And for luxury cars, Smith sold $58,000 and Jones $32,500. To find the total sales, we will add matrices. The numerical data is the same size, 2 by 2. So the sum is defined. For the sum to be meaningful, however, the labels have to match so that we know what the rows and columns mean in the answer matrix. In the August matrix, the rows name the salespeople, and the columns represent the car types. In the September matrix, the rows represent the types of cars, and the columns name the salespeople. If you haven't already entered them, label and enter matrices August and September with their row and column labels. We will leave the August matrix as it is. In order for the labels to match, we will take the transpose of September. So let's label and create a new matrix called as transpose. So if we want labels like August, we will type S to the T power equals in cell A9, skip a space. We will type our row and column headings, economy for the column, and luxury, and the salespeople for the rows, Smith and Jones. So we'll highlight the 2 by 2 array and type equals transpose, parenthesis, and we want to transpose the numerical data in the September matrix. So that is C6 to D7, close parenthesis and hold down Shift and Control and hit Enter. And you can see that what was in the row for economy is now in the column for economy, and what was in the row for luxury is now in the column for luxury, and so the matrix and the labels, the size, all match those of the August matrix. Let's label a new matrix now called total sales. Widen column A a little bit. And we'll need the same row and column headings as in the earlier matrices. Economy and luxury. And the row headings Smith and Jones. We'll now highlight a 2 by 2 array for the numerical data. And we said we wanted to add the two matrices, so we'll type equals parenthesis C2 colon D3 close parenthesis plus, oops, I typed a plus, backspace equals. And for the transpose matrix for September, parenthesis, we have C10 to D11. Remember to hold down Shift, Control, and hit Enter, and the calculation is complete. The result includes the row and column labels like the August matrix. We see that Smith sales were $87,400 from economy cars and $145,000 from luxury cars, while Jones sales were $136,500 from economy cars and $102,500 from luxury cars.
A lawnmower manufacturer operates 3 manufacturing plants and produces 4 types of lawnmowers: mulcher, bagger, riding, and stand-on. The number produced at each facility for the upcoming week is shown in the table. Notice that in the first table, the row labels are plant locations. We have the east plant, the central plant, and the west plant, while the column labels are mower type: mulching, bagging, riding, and stand-on. So the table tells us that in the east plant location, each week they produce 20 mulching, 50 bagging, 60 riding, and 30 stand-on mowers. The central plant each week produces 30 mulching, 60 bagging, 40 riding, and 10 stand-on mowers, and the west plant produces 20 mulching, 40 bagging, 50 riding, and 40 stand-on mowers. The next table shows the week's cost in dollars for materials and labor associated with producing 1 unit of each type of mower. Note that the row labels are the mower type, the mulching, bagging, riding, and stand-on, and the column labels are cost type, materials and labor. So the table tells us that a mulching mower takes $1,200 in materials and $2,000 in labor. A bagging mower takes $1,100 in materials, $2,000 in labor. A riding mower takes $2,000 in materials and $3,000 in labor. And a stand-on mower takes $2,400 in materials and $3,200 in labor. We want to find the total production cost for material and labor at each plant. Let's create matrices P and C to represent the production levels and costs respectively. So we're going to create matrix P equals, and since we just typed in numbers for matrix P, we can go back to the production level and copy the numeric entries. So we can go to highlight, go to copy, go to the first cell where you want to place the new matrix, go to edit, paste, and we have the values now entered for matrix P. Notice that P is a 3x4 plant location by mower type matrix, and we want to widen the cell just a little bit so we can see it. Okay. Now we need to create matrix C, our cost matrix, and again we're going to copy the cost material from our other matrix. So we highlight the information, we do edit, copy, go to the first cell that we want the information in again, and then do edit, paste. C is a 4x2 mower type by cost type matrix. We'll use multiplication to get the results that we want, since total cost is equal to number of units produced times cost per unit. We're going to check the size and row and column labels to see if multiplication is possible. If we look at the dimensions, P is 3x4, C is 4x2. Since the inner dimensions are 4 and correspond, then the product exists, and the dimensions of the result will be 3x2. Then we check the labels. P is location by mower type, and C is mower type by cost type. The inner dimensions are mower type for both, so logically we can perform the product, and the result will be a location by cost matrix. Now we're going to label PC, P times C, and we need to highlight a 3 by 2 array. To hold the product, we type the formula equals MMULT parenthesis, go to matrix P, select the location, and it's in B12 to E14, comma, now we do C, which is in B17 to C20, do Control Shift Enter, and we get resulting matrix P times C. Now, maybe a little hard to read this and know exactly what each of these numbers mean, so we're going to place this back in a labeled matrix form. So we're going to enter it in. We're going to label our rows as plant location. We have the east plant, the central plant, and the west plant. And we have materials and labor. Now we want to copy this material P times C into this matrix. Before we copied, and we just used a copy and paste because we were copying from typed in data, but now we're going to be copying from an array. So we're going to go up and highlight the cells in the array, and we're going to go to Edit, Copy. Now we want to highlight the same size array in our new location, and we want to go to Edit, Paste Special, and under Paste we want to select Values and click OK. That pastes number values into our array for that we can edit if we want to. So we have a couple of the numbers with no commas, so we can edit and type those in because we now have number values. This tells us that 1 week's production cost at the East plant is $271,000 for materials and $416,000 for labor. At the Central plant, $206,000 for materials and $332,000 for labor, and at the West plant, $264,000 for material and $398,000 for labor. To summarize, using Excel to perform matrix multiplication A times B, 1. Enter the matrices including labels. Be sure that the size, type, and order of column labels on A match the row labels on B. 2. Highlight the cells for the resulting matrix and type the formula to multiply A, array 1, times B, array 2. The command is equals MMULT, parenthesis, array 1, comma, array 2, close parenthesis. 3. Hold down Control, Shift, and hit Enter to complete the calculation and write the solution. Use Excel to find the determinant of A where A is equal to the 4x4 matrix with row 1, 1, 2, 0, 3, row 2, 0, 4, negative 2, 5, row 3, 0, 5, negative 2, 4, row 4, 0, 0, 0, 3. First, let's be sure the determinant is defined. Since A is 4x4, it is a square matrix and does have a determinant. You may put the matrix in any location, so the arrays in your commands may differ. As with any matrix operation, you need to label your result. So we're going to type in det parenthesis A equals, for our label for our determinant, and reserve space for an answer. Since the determinant of a matrix is just a number, you can simply type the formula into a single cell. We're going to click on cell B6 and put in the formula to perform the calculation. We're going to type equals MDETERM, open parenthesis. We're going to identify our matrix. Our matrix A is in cells B1 to E4, close parentheses. To complete the calculation, hit enter. Yes, that's right, just hit enter. This is a single cell. The answer is a number, not a matrix, so we do not have to use the array command. Of course, you can hit Control, Shift, and enter simultaneously if you want. That also works. The result is determinant of A equals 6. Now let's look at another example. Find the determinant of matrix C equals, in row 1, -3, 2, -1, in row 2, 2, 3, -1.5, and in row 3, 4.2, -2, 1. First, be sure that the determinant is defined. Since C is 3 by 3, it is square and does have a determinant. So we're going to label determinant of C equals and we type in the command equals MDETERM parenthesis, select our matrix, which is located in cells B1 to D1, close parenthesis, and hit enter. We get determinant of C equals 0. Remember, 0 is just another number, so matrix C does have a determinant, and the value of the determinant is 0. Let's look at another example. Find the determinant of n if n is, in row 1, 1, -6, 2, and in row 2, -4, 2, 1. First, let's be sure the determinant is defined. Matrix n is 2 by 3 because it has 2 rows and 3 columns. It is not a square matrix, so n does not have a determinant. If you try to use Excel to find the determinant, you'll get an error. Let's see what that looks like in Excel. We're going to label determinant of n equals, and we want to type equals MDETERM parenthesis, highlight our matrix. It's in cells B1 to D2, close parenthesis, and hit enter, and we get a strange symbol. Looks like £, value. This means there's an error. Since we did not get a number, we got an error signal. There is no determinant for matrix n. The determinant of a square matrix is a function that has many useful applications. You saw one of those applications about inverse matrices in an earlier lesson about determinants. The remainder of this lesson focuses on that application, using the value of the determinant of a square matrix A to discover if A inverse exists. Given a square matrix A, if the determinant of A is not equal to 0, then A inverse exists. If the determinant of A equals 0, then A inverse does not exist. You will see more about determinants and inverses with another application in later lessons. We will look at matrices we used earlier in this lesson. Relating the determinant to the existence of an inverse. Let's look at the matrices we used before. We're going to begin with matrix A. Recall that A did have a determinant. The value of the determinant is equal to 6. Since determinant of A is not equal to 0, matrix A has an inverse. Now let's look at matrix C. Matrix C was square. It had a determinant. The value of the determinant was 0. Therefore, matrix C does not have an inverse. Now let's look at matrix N. Matrix N is 2 by 3. It is not square. It does not have a determinant and therefore does not have an inverse. In summary, in this lesson you learn to find the determinant of a square matrix and to use the determinant to find whether or not the inverse of the matrix exists. Be sure that the matrix is square first. Next, enter the matrix. Next, click on a cell, type the formula, equals MDETERM parenthesis, your array, parenthesis, and press enter to complete the calculation. And remember last, if determinant of A is not equal to 0, then A inverse exists, and if determinant of A equals 0, then A inverse does not exist.
Finding the inverse of a matrix using Excel. The process is best shown with an example. Our example matrix M is in the spreadsheet. The first row is 1, 5, 1. The second row 2, 2, 1. The third row -1, 4, 0. First we need to decide if matrix M has an inverse. So we will find determinant of M. Since M is a square 3-row by 3-column matrix, you can find the determinant. You may put your matrix in any location, so the array in your command may differ. We'll label DET of M equals, and since the determinant is just a number, we only need one cell, and we'll type the formula equals M DETERM of, our matrix M is in cells B1 to D3, close parenthesis, and hit enter. Or you can also use Shift Control Enter. The determinant is equal to 1, so that means M has an inverse because the determinant is not equal to 0. Now we'll find the inverse of M. So we'll label M to the -1 equals we need a 3 by 3 space for M inverse because M is 3 by 3 and the matrix and its inverse are the same size. We'll type the formula immediately, M inverse parenthesis and the array for M from B1 to D3, close parenthesis, and in this case we must hold down Shift and Control together and hit enter in order for the result to appear. So the inverse of M is in the first row -4, 4, 3, in the second row -1, 1, 1, in the third row 10, -9, -8. If the solution is correct, then M multiplied times M inverse must give us the identity matrix I. So let's multiply M times M inverse. Since both are 3 by 3 matrices, the result will be a 3 by 3 matrix. And if I want to type in M and then times M inverse equals, I'll highlight the 3 by 3 space and immediately type without clicking equals. Remember, multiplication command is MMULT. The first array, which we put M on the left, so we'll highlight M first, comma, and M inverse second on the right. Put in the parenthesis, hold Shift Control and hit Enter, and as expected, we got the identity matrix 1 0 0 in the first row, 0 1 0 in the second row, 0 0 1 in the third row. Do we get the same identity matrix when we multiply M inverse on the left times M? Let's see. M inverse times M equals. We'll highlight our 3 by 3 array and type without clicking equals M U L T, open a parenthesis, and I can move back up to find M inverse here, then a comma. I'm using the scroll bar to go back up to select matrix M. Go back down and see if my entries are correct. So I have the correct arrays, close a parenthesis, Shift Control Enter. Now this is unexpected. I did not get the identity matrix that we had before. I got these entries here, and that middle column, this entry and this entry look very odd. What do the numbers mean? They are in scientific notation. Due to rounding within the software program, the exact value of 0 is often not produced. This is relatively common when calculations are done by a computer or a calculator. Let's take a closer look at the numbers. 1.776 E-15. You're more familiar with the scientific notation, which would be 1.776 times 10 raised to the negative 15 power. That would be a lot of decimals, and so this entry is basically 0. And the same down here. Negative 7.105 E-15 is the same as negative 7.105 times 10 to the negative 15th power. So that also is approximately 0. Whenever you see a number, E dash, and another large number, that's the same as the scientific notation, a large number times 10 to the negative large number power, and so we can assume that that is equivalent to 0. So these matrices are equivalent to each other. Let's look at our next example. We'll move to my worksheet B. Find the inverse, if it exists, of this matrix B. In the first row we have 1, 4, 2.7. In the second row, 4.13, 6, 5. In the third row, 2, 0, 1.5. And in the fourth row, 1, 2, 3. First, we need to decide if matrix B has an inverse, so we will find determinant of B. But B has 4 rows and 3 columns, so it is a 4 by 3 matrix and it is not square. So neither the determinant nor the inverse exist. So we can say that since B is not square, there is no inverse for matrix B. And we move on to our next example. Matrix C. Again, we'll find the inverse, if it exists, of this matrix. The first row, negative 3, 2, negative 1, 2, 3, negative 1.5, 4.2, negative 2, 1. First, we need to decide if matrix C has an inverse, so we will find determinant of C. Since C is 3 by 3, it is square, and we can find the determinant. We'll label DET of C equals, we're on one cell, which is all we need for the determinant. So we'll take equals M, D-E-T-E-R-M, of, put in the array for matrix C, and hit enter, and we find that the determinant of C is 0. Well, matrix C has a determinant, but because that determinant is 0, matrix C does not have an inverse. Because the determinant is 0. Now, what would it look like in Excel if you tried to find the inverse of C without checking the determinant first? Well, let's label C inverse and try it. Since C is a 3 by 3 matrix, we have a 3 by 3 array to highlight, and we'll type in equals M-I-N-V-E-R-S-E, put in the array, remember to do Shift Control Enter, and we get a lot of # num parenthesis exclamation point everywhere. Clearly this does indicate an error, and there is not an inverse matrix there. So when we found the determinant equal to 0, we knew there was no inverse. To summarize using Excel to find the inverse of a matrix, first, enter the square matrix. Second, find the determinant of the matrix. If the determinant is not equal to 0, then A inverse exists. If the determinant equals 0, then A inverse does not exist. Third, highlight the cells for the resulting matrix, type the formula equals M inverse parenthesis array end parenthesis, and hold down Control Shift and hit Enter to complete the calculation.